Good morning to all. In this video we continue with the CDC solution designs. It is a part 6 and it is for multi-bit data transaction across the asynchronous clock domain. So in this part we are going to see this handshake-based synchronization, and please refer my earlier VCS and design vision videos for the to get the more idea about this process, how we can simulate and synthesize using the design vision. So the basic block diagram of this handshake synchronization is shown as let's say there is a data inputs and data output. This is a bus, and this is a D flip-flop registers 8-bit, and this is a sender logic and this is a receiver logic. So once we load the data using this load signal, data is present on this bus, and as soon as this sender logic get the enable signal as a load, it will send the request using the 2 flops synchronizer to the receiving logic, and once it is received as a request, it is sample the output flops DFF81, and we get the data from this flop or register. And once we strobe that or sample that data bus, we send back the acknowledge signal to the sender logic. So in this way the complete transaction of data is happening here. So we have separate clock A, clock B, and the reset, load, and the strobe. Using the load and strobe, we can have the sequential or the consecutive data transaction using some logic at the sender and the receiver side. So this is one of the case where the clock A is lower than the clock B, and from this diagram we can clearly see that the data is getting at the receiving domain. Okay, so I don't think we find any issue with this because it is very well synchronized. The second case is that when the clock A is faster than clock B, still we get the data. Okay, actually this is a simulation based waveform, so we try our best to get this in post synthesized waveforms. So for the process of the synthesize and the simulation on VCS, we need a file list. So for this synchronizer, there is a files like a test bench file, then the HS synchronized one is a over top, and DFF1, the DFF81 sender logic and receiver logic, and one reference model for 90 nanometer. All these are listed in this all files.txt. We will see one by one. The folder details we already seen in earlier videos. The code folder contains all the resources of the files or source files. VCS folder contains the Makefile for the simulation and using RTL as well as synth. DC90 having the TCL file for the synthesis process on the 90 nanometer. Work folder from where we actually run the design vision for the synthesis. There is a result folder. Under that there is a DC90 folder where the synthesized results or get netlist is stored there. Obviously there is a file list which is already we seen all files.txt. So for the design vision setup is simple. We take the reference of 90 nanometer, and all the codes are resided under the code folder, and there is one file list where all the parts of the files are listed as we see in this presentation. So the command is simple. This is shell -f tickle file path, and we set the my top equals to the hs-sync1. This is for the synth simulation actually based on the RTL. Having the same command we already seen. This is for post synthesis simulation. So we just, and please subscribe my channel, like, and make any comment for any requirements. And if you want some files or something like that, just mail me at yours tm12 at gmail.com. Okay, so just mail me. I will send the files if you require. Okay, so we back to the terminal where we can see all these files one by one, and make files and the tickle files as well. So we go with the code folder. So in that there is a one tbhs. This is our test bench for the handshake-based synchronizer. Okay, for the changes for the low and high frequency or greater or smaller frequency, we have to change here. Okay, we take the 6 repetition of the load and stroke kind of things. Okay, this is our main top. So we just quickly view the top. So this is our top. Okay, which has instantiation of the DFF 1 and 81, then sender logic and receiver logic. So as we saw in the diagram, it is same implemented in using the instantiations. So basically the important part is DFF1 dot. This is a simple 2 flops. Okay, it is a synchronous reset. Then we can check the 81. It is 8-bit flop. Okay, quickly we see there is one receiver logic. Receiver logic is simple. Okay, once we get the request in, we acknowledge as well as enable. Okay, so again there is sender logic. Sender logic is simple. Once we have the enable, we place the request. Okay, so we need to go to the either VCS or design vision. So we check first the synthesis process. So we go to the DC90 where the RTL 90.tickle is there. Okay, this is the same RTL it is a tickle file. If you remember the design vision, it is the same tickle file I am using. Only the change is that we are taking the clock name as a clock A. Rest of the part is same. Okay, I just scroll for the ready reference with the screen. Okay, and we get the results at under the results folder, DC90 nanometer. Okay, also we pop up the result here also. You can pause and you can see what I write here. Okay. So quickly from the work folder, I just evoke the design vision and see the results. Okay. The command is same. DC shell have. Okay, this is the command. So this flag is meeting for the max, and this is for min. This is for setup. This is for hold. So it is a well work with the 100 nanometers. So we can also see the GUI start if we need so. Just for the sake of visualization, how it look like. This is symbol. Two clocks, load, reset, data in queue, stop, and also the schematic, zoom fit, and underneath of it we can also go inside of that. It is simple logic there. Okay, I hope you got the point. Anyway, we just check the GetNet list reports. This is for the all reports actually. This is a area report, power report, timing violation reports. Okay, setup and hold. Okay, we can exit from it. We can check the that GetNet list. What is that? It is sync 190. This is GetNet list created by the synthesis process. Okay. Now we quickly go back to the VCS process for the simulation, pre and post. We already seen the pre waveform, so we just go for the post synthesis simulation only. So for that we need to go VCS. And we can also have the look of Makefile. So this is a Makefile. We are taking the reference from the all files.txt, and there is one input, like whether it is for the synth or simulation, I mean RTL or synth mode. Okay, so for the synth we are taking the reference from the GetNet list at the result DC 90 nanometer, and for the RTL we are just taking the RTL reference for the simulation. So we quickly fire the command make top equals to, and then specify the mode like this. We are going for the synth process, so we can directly check with the sync. As we seen from this, we are actually compiling the what we required. So these are the files that we are referring for. Okay, so we get the pop-up of this file DVE for the simulation. This is top files names. We also check which top it is following, like okay. You can go inside one of the so I think it is for sync. Okay, I think it is taking this as a top because it is after this test bench file. So we just remove this from the all files.txt. Okay, and then we recheck it. So vi all txt, just comment it. Okay, now recheck with the synth. So now it is taking the get netlist. We once check this. Yes, it is from the synthesis get netlist. So anyway, Control A, Control 4, and hit F5. Zoom fit, press F. So this is our input. This is output, and this is strobe, and this is a load. So from this we can see there we can have the data transactions. There is some glitches are there, but still it's okay. We can have the stable data afterwards. Okay, I hope you got the point. The next video will be on the FIFO based for the data synchronization across the multi-bit signals. Okay, I hope you got the point. Anyway, we just wrap up this solutions videos as early as possible because we have other things to take it as design concepts. And please subscribe my channel. Thank you.